Hello and welcome to today's video where we will discuss the topic of stall from principles of flights. Before we jump into the questions that we have prepared here for today, which of course will be the most recent ones from EASA actual exams, I just wanted to give you a brief introduction into the stall before we go into the questions, and I'll give you some more details after. Remember that a stall happens when an aircraft stops producing lift, the wing stops producing lift, or at least stops producing significant lift as some lift will be there. Remember that stall occurs when the airflow separates from the wing, meaning now our wing is essentially falling down the air. The stall will happen after the wing exceeds its critical or stalling angle of attack. For the exams, remember that the critical and stalling angle of attack is still not stalled. The meaning at alpha crit, we will have the highest possible alpha. Anything afterwards, the aircraft will stall. Then also remember, especially for the exams, that a spin is also a stall. If we are going downwards in a spiraling motion, this will be a spiraling dive. And this will be everything for just a brief introduction, and I'll try to give you more tips and details as we go through the questions right here. So for the first question, a student pilot is performing slow flight exercise at a constant altitude. They reduce the speed whilst pulling back the stick to maintain altitude. As the aircraft has excellent stalling characteristics, the aircraft will eventually stall and start to descend at a constant speed. The pilot still pulling the stick backwards. Select the correct statement about the drag. So of course, for the exams, remember that the two key drags, parasite and induced, will be a function of airspeed. The parasite drag can be calculated using v squared and the induced 1 over v squared. This is because as we go faster, the parasite drag increases, and as we go slower, the induced drag will also decrease. However, in this case, this is a very interesting situation because as we are maintaining the altitude, this means that the lift will pretty much stay constant. In this case, however, we are slowing down, so the most sensible answer will be to consider the induced drag decreasing. And when it comes to, of course, parasite drag, it will be also decreasing because as our airspeed decreases, of course, so does the parasite drag. And for the induced drag, sorry, of course, it increases as it's the opposite as parasite. And then until the stall then will decrease slightly while the total drag continues to increase. And the reason for this is that after the stall happens, the parasite drag stops following the standard curve because now the surface of our aircraft will be much, much greater as all the wings and the fuselage will basically dropping down like a rock rather than going forward. So the area has greatly increased, meaning the parasite drag will also increase, adding up to the total drag of our aircraft. The induced drag increases because, as we just discussed, it is proportional to 1 over v squared. For question number 2, if the stall speed of an airplane is 60 knots, at what speed will the airplane stall if the load factor is 2? And there are quite a few questions in the exams which ask you to calculate the different stall speeds depending on the different conditions. Generally speaking, remember that your new stall speed will be the old one times the square root of load factor. In this case, it is very simple because load factor is given and it's 2, meaning square root of 2, 1.4 times our old stall speed 60 gives us 85 knots for the new stalling speed. However, some questions will not give you directly the load factor. They will give you, for example, the bank of your aircraft, because as you know, as we're banking, as we're turning, the stall speed also increases. In that case, remember that the load factor in bank will be 1 over your bank angle. So if you're banking at 30 degrees, this means 1 over 30, and then this under the square root times your old VS will give you your new stall speed. And lastly, remember, if weights are given in the exam, then you need to do a square root of your new weight divided by your old weight. So these are most of the cases that you'll see in the exams. Remember, square root of your old load factor will give you the multiplication for your old VS to calculate the new one. For question number 3, which statement is correct about the laminar and turbulent boundary layer? Of course, we have two main boundary layers, generally speaking, the laminar and the turbulent one. This is the air, the pocket of air that goes over your wing, and this is what will produce effectively the lift. The more energized the layer, the harder it will be for the layer to separate from the wing, meaning if the layer is energized, it has better stalling characteristics and will delay the stall. This is also why the aircraft will use slats, the front leading edge lift devices, because they re-energize the boundary layer. The same is true for the turbulent boundary layer. So remember, the turbulent boundary layer will have more kinetic energy, meaning it will be more difficult to separate it. However, laminar layer on top of the wing will decrease the friction drag, as it will be, simply put, smoother. So as we go through all the possible answers here, the separation point will occur earlier in the turbulent layer. This is incorrect. The more energized the layer, the separation point will occur later. Friction drag is lower in the laminar layer. Absolutely true. It's smoother, meaning the air flows, relatively speaking, better when the layer is laminar. Of course, friction drag is lower. This is the opposite and will be equal. This is not true either. Remember, the boundary turbulent layer will also be slightly bigger than the laminar one. Now for question number 4, how does the CG position relate to spin attitude of an airplane? Assume CG always remain in limits. And this one is quite intuitive as well. So you can think about fighter jets which have the CG more aft than forward in order to increase maneuverability. If you ever saw a video of a fighter jet stalling, it is very prone to a deep stall, meaning the aircraft will start speeding and stalling, being essentially flat. So having the nose at a horizon. And this is because the CG is more aft. As the CG is more forward, and this is also true for most of the trainer and GA aircraft because of the heavy engines in front, then the aircraft will tend to drop the nose down and the spin will have a nose down attitude. And this will help greatly in recovery, because this way it will be much easier to unstall the wing, as during the spin the wing is actually stalled. So going back to the answers here, the further forward the CG, the flatter the spin. Of course, it will be the opposite. So the further after the CG, the flatter the spin attitude. And this is absolutely true. And if you visualize it, this will actually make a lot of sense. For this reason, some of the older aircraft like the F4 Phantoms, for example, they have a chute in the back. So in case of a spin, they can deploy a parachute, which helps to put the nose down, because with the CG position aft, it is very hard to put the aircraft back, especially when the flight control surfaces are also stalled and inefficient. For question number 5, what are the possible consequences of climbing to high level using the Autopilot vertical speed mode? So this question is a bit of a blend between the instruments and the stall topic. However, it's very important to remember how the vertical speed mode works. So vertical speed mode, generally speaking, will try to keep your vertical speed constant. However, now as you are climbing, your engines will produce less and less thrust, meaning your airspeed will be slightly decreasing. So if that happens, of course, your vertical speed will decrease if you do nothing and you keep constant attitude of your aircraft. So the vertical speed mode, what it will do in order to keep constant vertical speed, it will keep pitching the nose higher and higher and higher as you climb, eventually depleting all your energy and your airspeed dropping below your stall speed, and in effect stalling your aircraft. So this is very important to keep vigilance or climbing with vertical speed modes, as this mode will keep the vertical speed no matter what, even if the aircraft approaches your stall speed. So it's very, very important to remember to monitor this, and ideally not climb with vertical speed mode when in high altitudes. So going into the questions here, increasing airspeed and the airplane may stall. It's the opposite. The airspeed is decreasing. Use of vertical speed mode is not permitted in climb. It is absolutely permitted and is very often used in the airlines in order to, for example, not trigger spurious TCAS alerts. However, decreasing airspeed and the airplane may stall will absolutely be the correct answer. As we said before, as we get higher and our aircraft drops the airspeed and the thrust is also lower from the engines, now the system will try to pitch up to maintain the vertical speed, even more decelerating our aircraft. And now for the last question about the swept wing. aerodynamics at a low speed, and the pitch-up phenomenon. So remember that the swept wing is prone to deep stall, and this is actually quite a big threat when it comes to flying swept wing, especially after flying square wings in the GA. In case of a swept wing, because the wing is further to the back and the downwash is different across the entire wing, the tips of the wing will actually stall first. This is also why there is some twist added to the wings in order to change these characteristics. So remember that the downwash will be highest at the wing root, and then it will consistently be lower at the wing tips. As the downwash is lower, also the effective angle of attack will be increased. So as the effective angle of attack is increased, it means that the alpha of the crit and above will be reached higher rather than in wing roots. This in effect causes the wing tips to stall first, and because they are more aft, now the center of pressure of our wing will move forward. And this creates a very dangerous pitch up moment of our aircraft's nose. So this will further prevent us from pitching down, or will require us to use even more force in order to pitch the aircraft down to regain the airspeed. So this is something that is very dangerous. In case of the square wings, of course, this is not the case. And in some cases, like the elliptical wing, the wing will stall almost consistently across the entire platform, making them generally the safest and most efficient. In this case, this switch phenomenon will of course be caused by the wingtip stall, as we just discussed. And lastly, remember that the deep stall phenomenon will also be very prone when it comes to T-tail aircraft, because the turbulent layer of the detached section of the flow from over the wing will start hitting the elevators, making them very, very inefficient, and in return making it almost impossible to recover because we do not have the control of the aircraft anymore. So this is everything. This will be the last question. I know the topic of stalls is very deep, and it has a lot of different situations and cases, and I'm sure we'll do another session in the future on this particularly. However, I hope this was helpful so far. If you have any questions, as always, feel free to ask, and we'll do our best to answer. And until then, I wish you all the best, and I hope you smash your future exams. So bye-bye.